We present EP2P-Loc end-to-end 3D point to 2D pixel localization for large-scale visual localization. In visual localization, when you input an image, and there is a given map in the form of a database, it estimates the 60 of camera pose that captured the image within the map. Typically, the problem of estimating the camera pose from 2D images is addressed using the perspective and point problem, often referred to as a PMP solver. To use the PMP solver, it requires having 2D coordinates in the image and their corresponding 3D coordinates. We were inspired by this problem and decided to undertake new research with the motivation by utilizing 3D sensors. However, due to the representational difference between 2D and 3D, it is challenging to match them. So, our first objective is to demonstrate the potential utility of 3D data generated by 3D sensors. Secondly, we aim to address the issue of poor matching due to the disparity in representations between 2D images and 3D point clouds. Lastly, our goal is to reduce memory usage and the search space to effectively perform large-scale visual localization using a novel end-to-end network. To evaluate this novel approach, we established benchmark datasets based on the 2D 3DS and the KITTI datasets. Figure A represents the refined dataset generated by the sensors, while Figure B generated through SFM. It is evident that our dataset is more structurally refined and contained fewer outliers. For the coarse-to-fine matching, we provide data where the global map is split into smaller submaps. To mitigate the representational disparity, we propose a simple module that removes the points not visible in the images. Using the camera interest parameters, we transform 3D points into camera coordinates and use the Z coordinate as steps. We then retain only the nearest points from the perspective of the image using mean pooling. Due to empty spaces, points behind words may still be considered, so we locally remove least distant points to enclose nearby points using max pooling. During the training process, both images and point cloud submaps are simultaneously inputted. We consider point cloud submaps within a 10-meter proximity to be positive examples, while submaps from different areas are designated as negatives. We tokenize the input image and employ an IPR module to the point clouds. Next, we extract local features through each transformer and extract global descriptors using Matplotlib, and these descriptors are utilized for global matching. We concatenate the 3D point descriptor and the 2D patch descriptor, then perform 2D patch classification using a score MFP. This process classifies which patch the 3D point belongs to if it exists within the image. This approach simplifies the matching problem, addressing it through a straightforward classification network. Additionally, it enables us to further reduce the search space. To obtain the features of each pixel, we employ positional encoding and utilize a simple two-layer MFP. The positional encoding is based on basic sine and cosine functions, allowing us to set the 2D pixel coordinates of the 3D point descriptor to the closest result. Finally, we locate the 2D pixel descriptor that is closest to the 3D point descriptor and construct the 2D 3D correspondences, which are then fed into a differentiable PMP solver for camera pose estimation. This enables the running of camera pose during the training process by minimizing the weighted reprojection error. The loss terms used for training are as follows. Alpha, beta, and gamma were all set to 0 to 5. We performed visual localization on the 2D 3DS dataset. Notably, our approach outperformed all experiments across the board, surpassing methods that rely on 2D matching. This experiment was conducted on the KITTI dataset. Even in the case of deep I2P, which includes a grid classification step in the middle, our model's patch classification exhibited more refined performance. Thank you.